Hello everyone, and thanks for watching Edupedia World Videos. This is a new chapter called Alternating Current, and up till now we've only seen currents created by batteries which flow at a particular value at any instant, but now we'll see a new type of current called alternating current. So the definition of alternating current is simply if the direction of current changes alternatively with time, right? So if this is, let's say, a graph for current versus time. So if the current were something like this, then this would also be considered an alternating current, because at some points the current is flowing in this direction and other points in this direction. In the circuit, it would mean if this is a circuit with various elements, sometimes the current is flowing in this direction, at other times the current is flowing in the opposite direction. This is something we haven't seen till now, right? But this is the generic alternating current. We won't study this. We'll study the easier version of this, which will always be a sinusoidally varying alternating current, right? Sinusoidally varying. That's just a fancy way of saying that it will behave like a sine curve. So the current which we will study, and as a matter of fact the current that is pumped into your house every day, is sinusoidally varying alternating current, and it would look something like this, like a standard sine curve. This is I, this is t. And we've already seen loops like this before in simple harmonic motion, and a lot of the terms we've used in simple harmonic motion will be same as the terms we use now. So the generic alternating current has an equation equal to I is equal to I naught sine of omega t plus phi. This is something we've seen before. I would be the amplitude of the current. Let me draw the graph properly now. If this is the graph, then I naught would be the amplitude of the current, whether positive or negative. Omega would be the angular frequency. The time period will be 2 pi by omega, because after t changes by 2 pi by omega, this whole term changes by 2 pi, which leads a sign back to the original value. So this is amplitude. Frequency, angular. Don't get confused by angular frequency and frequency. They are related by a factor of 2 pi. Frequency is denoted by nu, and it is equal to the inverse of the time period. The angular frequency is equal to 2 pi by the time period. And phi is the phase constant. We've seen this before in simple harmonic motion as well. Phase constant simply tells us what was the time when we chose t is equal to 0. If we chose this point to be t is equal to 0, then phase would be 0. If we chose this point to be t is equal to 0, then phase might be pi by 2. Right? So if t is equal to 0, I is equal to I naught sine phi. And that depends on where we choose our t is equal to 0 line. Right? Now, if I is equal to I naught sine omega t plus phi, then that must have come from a voltage that is also sinusoidally varying. So sometimes we'll write voltage as V naught sine of omega t plus phi. Now the important thing here is omega will be the same. If the current is changing its direction 50 times a second, it makes sense that that is because the EMF that is causing the current is changing its direction 50 times a second. Now, as we'll see later in this chapter and in these videos, these phi do not need to be the same. So we'll write phi dash here. The current could have a phase constant of 0, but the potential difference could still have some non-zero phase constant. In other words, the current could possibly be higher in phase or be lower in phase than the potential. Right. Before getting into the details, let's study some terminology related with sinusoidally varying current. So we will assume throughout this chapter that I is equal to I naught sine of omega t plus phi. So the first thing we need to know is average current. Average current is denoted by a bar on top of it. So this is equivalent to average current, and the definition of average current is integral of I dt by integral of dt from 0 to capital T. The lower term is just a fancy way of writing t, which is the total time. The average current will be the total current in one time period divided by the duration of that time period, right? So the lower term is just a fancy way of writing that this pretty much is equal to t, right? Integral 0 to d dt. Integral I dt means that every point we take the current, we multiply it by the small time, and we add it up, right? That's how we take averages. Now if you try to do that, I'm not going to do it, I hope you would, but if you try to do that, it will come out to be 0, because we know that the integral of I dt during one whole cycle will obviously be 0, because the upward direction covers as much area as the downward direction, right? And we can see that directly from the equation as well. Since the current's direction keeps on changing, the average current is 0. So the average current is not something which we can generally use to quantify this, but we would like to quantify this by a particular value. One thing we could do is we could quantify this by I0. That means saying the current is such that the maximum value is I0. But there is another easier and more useful way to quantify the current, and that is by using something called I square bar, which is called the mean square current. Right, so bar means average. So mean square current says exactly what it says, mean square current. It is the mean of the square of the current. Right, so if we just take the currents at different points and we calculate the average of those currents, that will come out to be 0, because we'll have just as many positive as negative currents. But if we take the square of each current and we find the average of those, that cannot be 0, because the squares will always be positive. Right, so I square bar is called the mean square current, and there's an so the definition of this will obviously be integral from 0 to capital T I square dt by t, or this term here. Right, so instead of taking the average of I, which will be 0 because it can be positive or negative both, we take the average of I square, that is obviously non-zero. Right, we'll calculate that in a second, but the most important term is called IRMS. And this is something which we've seen before in kinetic theory of gases. It is called root mean square current. It says exactly what the name suggests, the root of the mean of the square. You first take the square of the current, then you take the mean of that square, and if you take the square root of that, it is RMS. So this is equal to the square root of the upper thing, I bar square. Right, and this is something which we've seen before in terms of VRMS, which was the RMS speed of molecules kept in a container of gas. Right, so let's try to calculate the value of this. First, let's calculate the mean square current, that is equal to integral of I square dt by capital T, right, from 0 to t. We'll be assuming that I is equal to I0 sine of omega t plus phi, and capital T is equal to 2 pi by omega. So let's calculate this. This will come out to be equal to, I'll just write 1 by t outside, 0 to t, I0 squared sine squared omega t plus phi dt. Now what do we do when we have an integral of sine square? We turn it into the cos of twice the angle, right? We know that cos 2 theta is equal to 1 minus 2 sine square theta. Right, so what is sine square theta? It is equal to 1 minus cos 2 theta by 2. Right, so that's what we'll do here. So this is equal to I0 square by t, which we've taken common, 0 to t. Sine square of this whole thing will be 1 minus cos of 2 times omega t plus phi by 2 dt. Right. Now integral of cos of 2 omega t will give me a factor of 2 in the denominator, but in the value which we put, at one time t will be 0, which will give me phi. At another time t will be capital T, which will give me 2 pi plus phi. Right, so both the limits will be equal and the integral of this will be 0. We know that anyway. We take any sine or cosine, and if we integrate it during a time, during one whole cycle or during 2 whole cycles, which is the case here, then the integral will come out to be 0. So the integral of cos 2 omega t plus phi will come out to be 0. You can verify that yourself. So then all we are left is 1 by 2, integral of dt will be t, and we get I0 square by 2. this is equal to the average of the squares, which means that IRMS, which is the root of this thing, is equal to I naught by root 2. This result is why we did this whole business, because we wanted to calculate. I square is the mean square current. That is somewhat useful to us, but that is the square of the current. It does not even have the dimensionality of the current. We would like to have a value of the current which quantifies the value of this I naught sine omega t plus phi. The greater that value is, the greater the variation in current is. One thing could have been, we could have just taken I naught, but for reasons that will be clear in a second, we generally take IMS, which is I naught by root 2. So we could have a question in which we could say that there is a circuit with some elements and the current has an amplitude of 2 amperes, has an angular frequency of such and an initial phase of such. But more likely, instead of giving I naught, what they'll say is the current has a root mean square value of 5. If the current has a root mean square value of 5, then the amplitude is 5 root 2. Right? They are related by a factor of root 2. By the way, all this is same for potential as well. That means if we take V is equal to V naught sine omega t plus phi, then the average potential will be 0. The mean square potential will be V naught square by 2. And the root mean square potential, VRMS, will be V naught by root 2. That is the amplitude divided by root 2. Right. If you were to look at it in terms of a graph, this is the sine curve. These limits would be I naught or V naught, the amplitude. If we divide by root 2, we reduce it by a smaller amount and it will lie somewhere here. Right. So this I naught by root 2 or V naught by root 2, the root mean square, this sort of quantifies the strength of the electric current or the strength of the potential difference. Now, one of the major uses of this is anytime we need the square or the average of the square or the sum of the square, we can use the root mean square current. For example, if we wanted to find out the heat developed in a resistor during one time period, that would be integral of I square R dt from 0 to t. Right, but that I can directly write as, if I take R outside, integral of I square dt can be written as I RMS squared times t, and there's an R in the middle. Right, R is just there. If I RMS squared, which is the average of the squares, is equal to integral of I square dt by t, then integral of I square dt can be written as I RMS square t. Right, and this is the very simple result which sort of tells you why the root mean squared thing is important. The same thing we saw in kinetic theory of gases. That time we needed something that was the integral of velocity square, which came out to be kinetic energy. So we could easily write the kinetic energy in terms of the root mean square speed. Similarly, we can easily write the heat dissipated in a resistor in terms of root mean square speed. It is I RMS square RT. So anytime you want to calculate the heat developed, it will be the same as if there was no alternating current, just a direct current which had the magnitude IRMS. They would give the same heat developed. By the way, this everything is alternating current, but every current which we studied up till now is generally called direct current. So we moved away from direct current and I moved into alternating current. This is just to tell you the terminology. Right. So anytime we would want the heat developed in a resistor in one time period, it will be IRMS square RT. In that I square R, you can just write I square as RMS square. This is not just valid for one time period, it is also valid for times greater than a time period. So it is also valid for, let's say, 9000.1 time periods, because in that 0.1 variation will not matter. So it is valid strictly for one time period, but it is also valid for huge amounts of time. You will just have to replace this T by the actual huge amount of time. Right. The general supply which you get in your houses, the alternating current which you get in your standard switch, has a VRMS value of 220 volt. What that means is the amplitude V naught is root 2 times VRMS, that is approximately 311 volt. So what you get in your house is 311 sine of omega t plus phi. The time period is also usually quite small, around 60 times a second or something like that. Right. So 1/60th of the second, that's around what the time period is. right? So again, whenever you see voltage mentioned of a bulb or something and it is written 220 volts, you know that it's the RMS value, and that's why the RMS value is used to tell. Unless something is specifically specified, if they tell you that an alternating current with a voltage of 220 volts, that is the RMS voltage, not the magnitude, right? The RMS voltage is used to quantify this. So let's see what happens in simple circuits. The schedule we'll follow in this chapter is we'll do a simple R circuit, C circuit and L circuit. Then we'll do a RC circuit, LC circuit and LR circuit. And finally we'll do an LRC or RCL or whatever you want to call it circuit. LCR circuit is what it's sometimes called. Right. So in this video we'll do these three, and in the second part of alternating current, that is the next video, we'll do these combinations. Right. Once you understand these three simple ones, then it's only a matter of adding them up in a particular way to get what happens when you combine them together. Right. So let's study these. Let's study the simplest one, that is the current. Right. Let's see what our goal will be in all of these circuits. The goal will be if the EMF produced by the battery, now this will not really be a battery, it will be a source, would be E0 sine of omega t. That means we've taken the time to be 0 when at some instant when the EMF was 0. Right. So we'll not take a phi in this case. If E is equal to E0 sine omega t, that means the current in the circuit will be I0 sine of omega t plus phi. And what we need to do is find I0 and phi. This will be our goal for every circuit. So let's see this for the simplest circuit, a resistance circuit. In this case, we'll have a battery and a resistance. Except when you're talking about alternating currents, you don't have a battery, you have a source, an alternating current source. And they are generally denoted in a different manner. So this is the way alternating current sources are generally depicted in a circuit. Notice that this doesn't have any particular sign to it. When we had a battery, there was a positive and a negative side. In this case, current will equally flow to the right and the left side because it's going to be alternating current. This is the symbol for an alternating current source. Right. So in this case, what will be the equation? We go from this point to this point, the EMF is E. We go from this point to this point, EMF is reduced by IR, so minus IR, and then that is equal to 0. Right, because we've gone through this using KCL. That just gives me I is equal to E by R. This is as simple as it could have gotten. Right, that means I is equal to E0 by R sine omega t. Now we compare this to this. What we'll see is I0 is equal to E0 by R and phi is equal to 0. Right. So again, this goal is what you need to understand. We'll do in every case. And in the next case, we'll attach a capacitor, then an inductor, then an inductor and a capacitor, then all three of them. Right. But in the all cases, they'll be attached in series and they'll be attached to an alternating current source. The alternating current source will be assumed to have this equation. And based on that and whatever terms are there, whatever components are there in the circuit, the current has to have a structure like this. Right. Now all we'll need to do is find the values of E0 and phi. For the case of a pure resistor, I0 is equal to E0 by R. We need to find I0 and phi. So I0 is E0 by R and phi is 0. That means for a purely resistive circuit, this is called a purely resistive circuit, by the way. There is no phase difference between current and EMF. Right. When the EMF is at its maximum value, the current is at its maximum value. When the EMF is at 0, the current is at 0. Right. So there is no phase difference between them. The graphs would be something like this. If this was the graph of the EMF, then this might be the graph of the current. It might go upper and lower depending on the value of R and our chosen units. These would be two different units, but they would have the same phase. Right. So this is the easiest one. Let's move on to the next one, which is a capacitor. Again, I'll one more time write down our goal so that you understand it properly, because this goal is essentially the goal of this whole chapter and this video and the next video. So the EMF will be E0 sine omega t. That EMF will be created by a current source like this. And then to that we'll attach a number of things, either one or many things. In this case, now we'll attach just a capacitor. But whatever we attach, that will result in there being a current in the circuit, which will obviously be alternating again because the EMF is alternating. It will have a magnitude I0, which we'll need to find out what it is. Sine of omega t plus phi. So what we'll need to do is find I0 and phi in terms of E, omega, and R, C and L and whatever it is. So here it's C. So let's see what will happen in this case. We will go from this point to this point, we get E. We go from this point to this point, we get minus Q by C. Right? And we know that this is equal to 0. That means that Q, the charge on the capacitor, is equal to CE or C E0 sine omega t. So Q is in the same phase as the capacitor. As when the EMF is at its maximum value, the charge will be at its maximum value. And that makes sense because Q is equal to CE is a simple direct equation. From that we can get the current. What is current? Current is dQ by dt. The rate of change of charge on one plate, right? If this plate has charge increased by 2 coulomb every second, that means a current of 2 coulomb every second or 2 ampere is flowing through here, right? That will be equal to C E0 omega cos omega t, which is equal to I0 sine omega t plus phi if I0 is equal to E0 C omega and phi is equal to, now this is a tricky one, whether it be plus or minus pi by 2, that's what we need to see. So what is sine of pi by 2 plus theta? Is it cos theta or minus cos theta? Well, I remember that it is actually cos theta, right? These things you need to be very familiar with. So sine of omega t plus pi by 2 is cos theta, so phase is pi by 2. Right. So what this essentially means is, if we have E is equal to E0 sine omega t in a purely capacitive circuit, the previous was a purely resistive circuit, this is a purely capacitive circuit, then it leads to a current equal to E0 C omega sine of omega t plus pi by 2. Now it's your job to convince yourself that this equation is exactly the same as this equation, right? E0 C omega is the same, cos omega t sine omega t plus pi by 2. So for a resistor we saw that the current was simply the EMF divided by the resistance and there was no phase difference. Whenever the potential was at its maximum value, current was at its maximum value. Here it's completely different. Here the current is equal to the maximum current is equal to, this should be E0 by the way, the maximum current is equal to E0 C omega instead of being E0 by R. It was E0 by R for resistors and phi was 0 for resistors. But the interesting thing is, for a capacitive circuit, the current is not in phase with the voltage, it is actually ahead of the voltage by a phase of pi by 2. That means when the voltage is at its maximum value, the current is at its minimum value and vice versa. Right? They have a phase difference of pi by 2. So if the voltage would have a graph like this, then the current would have a graph like this. At t is equal to t0, the voltage is 0. What is the current at t is equal to 0? The current at t is equal to 0 will be E0 C omega, or the maximum value, or at t is equal to 0 sine pi by 2, again maximum value. So if this is the voltage, the current will be something like this. I apologize if the figure is not drawn properly in different places, but you get the point that the current will not be in phase with the voltage, it will be 90 degrees ahead of phase. The pi by 2, that means it is ahead of voltage. Right. Now I'm assuming by this time our goal has become clear to you, so I'll just do the last one in this particular video, that is a purely inductive circuit, and we'll really move on to the mathematics in the next video. I must warn you, however, in the next video there will be a fair bit of mathematics because it is important for me to derive all the formulas for all the circuits, show it to you, and then I'll show you a clever little trick so that you can remember all those formulas easily. So let's move on to a purely inductive circuit. Right, so we go from this point to this point, we get E. We go from this point to this point, we get minus L di by dt. What is our goal? We know that E is equal to E naught sine omega t, and we know that the current will have some form of I naught sine omega t plus phi. All we need to do is to find out the value of I naught and phi. Right. So E minus L di by dt, that will be equal to 0 by Kirchhoff's voltage law. From that we will get L di is equal to E dt. What is E dt? E naught sine of omega t dt. Now again it's quite easy, we'll just integrate. Initially the current was 0, finally it's I. Initially the EMF was 0, finally it's E. Initially the EMF was 0 because we've chosen E naught sine omega t. Hang on, I made a tiny mistake here that could lead to a lot of problems. What I did was I automatically assumed that the current is 0 at t is equal to 0. But that assumes that the EMF and current are in phase, whereas they may or may not be. So the correct way to do it would be to assume that there is some I dash. I can't use I naught because I'm using it here. Let's say I1, that's more natural. Some I1 will be the current at t is equal to 0. Right. So what that gives me is L times I minus I1 is equal to E naught by omega. Integral of sine theta is minus cos theta. So here it will be 1 minus, this is t, I don't know what I'm doing, I'm sorry, this is t. This will be 1 minus cos omega t. Right. So this is the equation. If we rearrange it a little bit, we can see that I is equal to minus E naught cos omega t by omega L plus E naught by omega minus Li plus Li1. Plus I1. Yeah, this is what it is. Right. Now, this is basically the answer, except there's a little bit of trick we can use here to calculate the value of E1. We don't know what E1 is yet, right? So the average of the current has to be 0 over one time period. We know that. The average of this term is 0 over one time period because it's cos omega t. We know that. Since both these terms are constant, the average over them has to be 0. That automatically means that this whole term is equal to 0. That means I1 is equal to minus E naught by L omega basically. The point is, I'll repeat it again, the average of this is 0 over one cycle, the average of this is 0 over one cycle. That means the average of this constant should be 0 over one cycle. But if the average of a constant is 0, then the constant should be equal to 0. Right. Also, we'll have minus cos omega t. What can we write minus cos omega t as? We know sine of omega t minus pi by 2 is equal to minus cos omega t. Right. So minus cos omega t can be written as sine omega t minus pi by 2. So the final result we get, I'll write it here, is I is equal to E naught by omega L sine of omega t minus pi by 2. That is equal to this, where I naught is equal to E naught by omega L and phase difference is equal to minus pi by 2. Right. I'll just write all three of them once more so that you get an idea. E is equal to E naught sine omega t means I is equal to I naught sine omega t plus phi. Right. If it is a resistive circuit, then I naught is equal to E naught by R and phi is equal to 0. If it is a capacitive circuit, then I naught is equal to E naught omega c, which is sometimes also written as E naught by 1 by omega c. We'll see why in the next video. This is just a fancy way of writing this. And phi is equal to pi by 2. The current is ahead of the potential difference by a factor of 90 degrees. For a purely inductive circuit, I naught is equal to E naught by omega L and phi is equal to minus pi by 2. So for a capacitive circuit, phi is greater by pi by 2. That means the current leads the potential difference by pi by 2. In a purely inductive circuit, the current lags behind the potential difference by pi by 2. And in a purely resistive circuit, the current and the potential difference are in phase. So for all three R, L and C circuits, we've been able to calculate I0 and phi in terms of E0, omega and L, R or C. So I hope this is clear to you now. In the next lecture, we'll complicate things even further. We'll consider RC circuits, then LC circuits, then LR circuits, and finally we'll consider an LRC circuit, which will be a combination of all three. Thank you.